welcome back people who keep coming, and there are a few new faces. So thanks for joining Space Cafe. And today we have a speaker who's actually visiting Japan for a couple of weeks. And so if you have any tips about what to do in Tokyo, please feel free to tell Danilo. So Danilo is actually from Brazil, and he's a postdoctoral researcher at Leiden University, Netherlands, and where I used to be. And he usually we have our speakers are usually for Space Cafe is from planetary science or astronomy, but today we have somebody special. Danilo's background is from philosophy of science. So, and plus Danilo was a teacher for a long time and a science journalist in Brazil, and now he's studying astrobiology and media, and how astrobiology is portrayed in the media. Like we have a project going on, and this topic actually his PhD thesis. So it's about the formation of solar system and planets, and the whole history, how these things came into place. And so it's kind of nice change from the science topics we have been listening. So we finally get a proper history lesson. So Danilo, you'll be in Tokyo until next Sunday.
Yeah.
Right? Yeah. So one more week to explore Tokyo.
Yeah.
And he's a drummer also, part-time drummer.
We're drummers.
Yeah.
Oh yeah.
Here you go.
Not me,
Yeah.
my husband.
No. And Danilo loves cats, but especially 3 cats. But all cats, but especially 3 cats. So if you have any recommendation related to cats and drumming, please do. So Danilo, welcome to Japan, and I'll give you the floor. Thank you.
Thank you, Tilina, for this very nice presentation. I really do love cats. I miss my cats. They are there in Brazil. I couldn't bring them to the Netherlands, and so I really miss them. But they've been very, very well there. Like people are looking for them. So don't worry about this. And also, Tilina didn't say I'm a horrible drummer. Not a proper drummer, a horrible drummer.
That's what all the good drummers say.
Yeah, from the Lars Ulrich school of drumming, right? Only they laughed again. Oh my God! Yeah, that is so horrible joke, right? So yeah, Lars Ulrich, the drummer of Metallica, he's a horrible drummer, but I idolized him nonetheless. Anyway, I have the controller here. Yeah. So, I did my PhD there at Unicamp, which is the University of Campinas, one of the top universities there in Brazil. It's a PhD on philosophy of science, but it is heavily historical, right? So, my background is not in astrophysics or any sort of natural sciences, but I was always passionate about astronomy, astrophysics, astrobiology. So that's why I'm currently researching there at Leiden how astrobiology is being portrayed in the media. And I'm also a science journalist there in Brazil. And although I don't have a background on natural sciences, I took the challenge of doing a thesis about the history of a field of natural science. Is very hard to do. I didn't know initially the amount of challenges I was going to face, but I think it was worthwhile. I won't say I enjoyed doing this work because it was very difficult to do, but at the same time I am very, very passionate about the subject. I think the subject in itself is very, very beautiful, very moving. And it also has a lot of repercussions to philosophy in a broader sense, not only in philosophy of science, but more general philosophy, right? I hope I can, show some of these things to you, right? So, we're going to start our history with, with the beginning of the concept of a solar system in the Copernican revolution, and since the 17th century, some natural philosophers began to ask what is the origin of the solar system, how the solar system have formed. And the amazing regularities that the solar system shows, like the coplanarity of the orbits, the fact that the planets orbit in the same orientation and so on, this usually, they gave the natural philosophers a hunch about a common primordial cause, as Laplace says. So in the late 18th century, you have, some first examples of some natural philosophers trying to explain the origin of the solar system. And Swedenborg from Sweden, and Kant and Laplace themselves, and Herschel himself, also William Herschel, great English astronomer. This image is Herschel's. It's an image showing a lot of different nebula, right? And all of them came up with some form of explanation that included a giant cloud of gas collapsing, beginning to rotate. And because of that, because of the law of conservation of momentum, this cloud starts to rotate, and it starts to leave, like rings of matter. And in these rings of matter, the planets begin to form, right? And this is, in a nutshell, the nebular hypothesis. It's a completely qualitative explanation. And it came out, in Laplace's case, it came out in one of his classic works at the end of the 18th century, and he kept, updating this at the beginning of the 19th century. And this explanation turned into the dominant explanation throughout the 19th century, right? And on top of that, the nebular hypothesis gave a general framework, inspired a general framework that underpinned the evolutionary worldview of European culture in the whole of 19th century. And this evolutionary worldview is very linear and progressive. So you have, at the beginning, the giant gas cloud, and it goes into stages of formation. Then the pinnacle of creation is the white European man, right? Yeah, and it also, it's not that it inspired the worldview of plurality of worlds, in which people from the 17th century started to wonder if other stars could have planets in their orbits, right? That is one of the major consequences, philosophical consequences of the Copernican revolution, that people started to wonder if other stars like the sun could have planets, right? So, but the nebular hypothesis reinforced this view of the plurality of worlds because it pointed to the possibility that all stars, all the process of formation of stars included the formation of planets around them, right? So if that was true, all of the stars would have planets around them. So the only observational support that the nebular hypothesis had during the 19th century were what they called the spiral nebulae. And just to go back a little bit, Kant was one of the first thinkers that came with the idea that these objects were in fact island universes, what he called island universes. Do you know what were the island universes, what he was talking about? He was talking about galaxies, right? he was saying that these objects are analogs to the Milky Way. They are very far away. They are extragalactic objects. This was in the middle of the 18th century, right? And curiously, this work, Kant published this work, and then he moved on to do other more important things in philosophy. Sorry? Yeah. And he published this work in 1755, if I'm not mistaken. And it never got, any readership at his time, because the publishing house just failed afterwards. And so, but afterwards, in the 20th century, Kant's view was rediscovered. And then because of that, you would find a lot of science popularization books saying that the dominant explanation for the origin of the solar system in the 18th and 19th century was the Kant-Laplace hypothesis. But Laplace had never heard of Kant's hypothesis. But they are they're strikingly similar, right? But anyway, in the middle of the 19th century, these objects, the spiral nebula, which we know today that they are galaxies, right? They are spiral galaxies. They couldn't know that they were spiral galaxies. There was no way of telling if they were extragalactical orbit objects or if they were inside the Milky Way. And they were regarded as possible evidence of solar systems formed elsewhere. So they were regarded as observational support for the nebular hypothesis, right? But the nebular hypothesis had a very deep problem in its core, which was the paradox of angular momentum. So if that giant cloud starts to collapse and starts rotating, what you're going to end up with, even if you form planets around, the sun would have to spin a lot faster than it spins today. Today, most of the angular momentum in the solar system is with the gas giants, not with the sun. The sun spins very slowly if the origin of the solar system is, in fact, a collapsing gas cloud. And the astronomers began to be aware of this problem around 1860, in that decade, right? Even then, they didn't have any other sort of good alternative, so they stick to the nebular hypothesis, but there weren't many professional astronomers looking into this problem. There were other interesting, more tractable problems, right? But because of the problem of the paradox of angular momentum, it began to grow, there were some tentative alternatives in the 1860s that began to deal with the concept of star collisions or grazing collisions or close encounters of stars being in the origin of the planetary systems. And these ideas, some researchers at the beginning of the 20th century, they started to develop these ideas. And what happened is that in a very short way of telling things, is that at the beginning of the 20th century, both in America and in the UK, you had examples of encounter theories. So this first one is a graphical representation of the so-called planetesimal theory. Planetesimal, does that ring a bell with you now? Because in the current framework, you have a central thing is the accretion of planetesimals to form the planets, right? So accretion of solid bodies to form, at least form the terrestrial planets and to form the core of the gas giants or even the icy giants, right? But it was originally developed, this idea was originally developed to deal with what would happen if a star or an object of similar mass passed by close to the sun and was capable of getting matter out of the sun, and this matter was going to cool down around the sun, start to rotate around the sun, cool down, and then starts to accrete in planetary cores. So the funny thing is that the birth of a major idea in the formation of planets today was in a very different context, with a very different concept. But this had a very, very deep effect on the beginning of the 20th century, philosophical effect. It was that it fostered anti-pluralistic views among the scientists. This means that the scientific community at the beginning of the 20th century, in the first half of the 20th century, they were dealing with, they didn't have certainty about this, but they were inclined to think that planetary systems are exceedingly rare in the universe, because encounters like this kind were exceedingly rare. They already knew that this kind of thing was exceedingly rare because of the space that separates the stars, right? And this gives birth to something that is going to have repercussions for the rest of the history, which is, it gives birth to a classic categorization of theories that separate the theories into two major feuds, opposing feuds. The first one is the monist theories, which are the theories like what Laplace proposed, which means that one and only primordial cause, one and only process being responsible for forming the planetary system, and dualistic theories, which were like they dealt with a concept in which you needed an external entity to interact with the sun to give rise to the planets. So dualistic because you need more than one cause, right? And the origin of the sun is then removed from the origin of the planets. The planets are not now being viewed as byproducts of the formation of the sun. The planets are viewed as products of a catastrophic event, a very rare event. And this is why you don't have a lot of speculations among scientists in their area about the existence of extraterrestrial life, right? So you had a very pessimistic view about the possibility of extraterrestrial life in the first half of the 20th century. When I started to be interested in this specific topic because I was writing my master's thesis about how Carl Sagan viewed science and so on, and I was in the library and I found by chance a book called The Mysterious Universe by James Jeans. James Jeans was the Carl Sagan of the beginning of the 20th century. He was a writer, prolific writer. He was an accomplished scientist, and he was going to radios and so on, like a very popular guy. And he wrote a lot of popularization books, and in the first chapter of this book, and I went to read this book, is from the 1930s, he states that the solar system got is the result of a freak accident. So we must be the only ones in the universe. And he kept his view until his death, with some modifications, right? So they dominated the first half of the 20th century, this theory. But then some things start to happen. First of all, we have the resolution of what is called the Great Debate, which is in the 1920s. They still didn't have the means to distinguish if the spiral nebula were galaxies. But then Edwin Hubble discovered a variable Cepheid in Andromeda, And by that, he could calculate the distance of the Andromeda Galaxy to us, and then he was certain that the Andromeda Galaxy was in fact a galaxy. Then people started to talk about the Andromeda Galaxy and not this Andromeda Spiral Nebula. It was only in the 1920s. This is, it's striking that, something that is at the core of the modern astronomical view is something so young, right? Something so young. Now, this view of the universe that we have is very young, very young. And in the late 1930s, you have some criticism from some very famous scientists now, that Henry Norris Russell and Lyman Spitzer. They definitely refute the encounter theories on different grounds, and we end up with no theory whatsoever about the origin of the solar system. And then we start to go back to a scenario which scientists begin to deal with. Well, what if we have, kind of a collapse of a cloud again? Let's try to explain the solar system with those concepts. So I'm not going to go into any detail about this stuff, because I could go into some very long detour here, and I would never finish this presentation. But the fact is that the main problem that was the discrepancy of the distribution of angular momentum in the solar system, the fact that the sun rotates very slowly, began to, let's say, scientists began to devise alternative explanations for it. So in the 1940s, the Swedish Hannes Alfvén started to develop a whole field called magnetohydrodynamics, and this led him and other scientists to come up with the idea of magnetic braking, which means that if you have ionized matter in the disk, then the magnetic field of the sun would couple its lines with that matter and would transfer angular momentum to the disk. And then the sun would lose angular momentum and transfer this angular momentum to the bulk of the disk, which were going to form the gas giants, right? And then in 1950, precisely that, another famous astronomer called Otto Struve, he observed a correlation between the stellar age and the rotational speed of the stars. So he was able to tell that the older the stars, the slower they rotate. So there must be a mechanism of slowing down the rotation of the stars. So that could tell, something about the origin of these objects also. And what is something that is very striking is that only in the 1960s you begin to have a community of scientists, of professionals, looking into this problem and starting to collectively examine the problem and say, well, let's try to solve this. Before that, you only had, individual scientists trying to explain the whole process, right? And that had a very, very important effect, right? And so this leads to a scenario in which the old idea of accretion of planetesimals that were, that was created there in the beginning of the 20th century, in a very different theoretical framework, started to be developed mainly by Russian scientists like Viktor Safronov, and there was also in the late 70s and the beginning of the 80s the Kyoto model here in Japan, the Japanese scientists like Hayashi, I don't remember his first name, but they started to develop this idea, started to do calculations to see how much time would it take for a planet to form from accretion of planetesimals. And they came up with a very good explanation for the terrestrial planets, but the more external planets would take, like 100 billion years to form, which is, of course, not adequate, or, like, it doesn't sum up with what the age of the universe is, right? So, and then this leads to a revolution in the 80s and the 90s, which is the observational revolution in this field. In the beginning of the 80s, you had this satellite that was launched by NASA called the Infrared Astronomical Satellite. And with this space observatory, they could, for the first time, observe what was the excess emission in the infrared around young stars. So this picture here, let's see if this works. Yeah, so this is a classic picture, but it is updated. I'm going to explain a little bit about this. So this is a disk of material, of solid material around a young star. Do you know what star is this? Have you ever seen this image? No? Beta Pig. Yeah, that's it's here, right? Yeah, this thing here, this small thing, is Beta Pig B. It's an exoplanet. This is an exoplanet, and this is the orbit of Saturn around the Sun. So this disk is something like 300 AU. 300 times the distance from the Earth to the Sun. This is the size of this disk. So just for perspective, Neptune is 30 AU from the Sun, right? So this is 10 times the orbit of Neptune, this disk. And there were 6 of these objects that were observed in the beginning of the 80s. They started immediately to be studied. Now, at that time, it was categorized as protoplanetary disks, which means that planets were forming there. Now it is categorized as a debris disk, which means that planets already formed or are in the late stages of formation here. Right? So this star has, I don't know exactly its age, but it is a young star. It's not a young stellar object. It is already in the main sequence, but it is a young star. So the process that we now know is that this debris disk will, with time, after some tens of millions of years, it's going to dissipate, because the big planets that probably exist around here are going to expel a lot of these materials, or are going to accrete a lot of these materials, right? And in the 90s, with Hubble, you had these beautiful images of what is called now propletes, but protoplanetary disks around young stellar objects in the molecular nebula of Orion. So it's a stellar nursery. If you Google it, you're going to see a lot of these objects. They are nascent solar systems. So this was a revolution, and this pointed the way, like for the community. But the community was already, going into the direction of developing the ideas of accretion of planetesimals and a protoplanetary disk and so on. But this, really was a game changer, right? And now what we have, with current technology, astrophysicists are able to observe in great detail these disks, these gas dust disks around young stars, right? So these images were produced with ALMA, a large interferometer in Chile, and they are interpreted not only as nascent solar systems, but they are now being, like studied in detail, in so much detail that, like scientists are able to capture planet formation in the process itself. This is what is called a circumplanetary disk. So there is a protoplanet here, and there is a disk of solid and gaseous material around this clump of matter that is probably going to generate moons around this giant planet, right? And this is something that scientists from a century ago would be completely. They were going to freak out if they were able to see those images, but yeah. So these objects are observed in there are so many of them, and they are being studied in so much detail that it's really hard to come up with a different concept that is not these things are formed by the collapse of matter around young stars, and then you're going to have planets as byproducts of the formation of the star in the center there. And here I'm going to enter a little bit of a discussion that is not I feel like this kind of thing is more relevant for history of science itself and philosophy of science than science itself. But anyway, it is an interesting discussion. So this guy is Stephen G. Brush. He's the main historian of the area. He has a trilogy of books on the historical development of this area, but he wrote these books, he published these books in the middle of the 1990s. So in a way it was kind of unfortunate because he published these books, which are seminal books. If you are interested in these books, you should read them, right? It is a very complete history of the field, very technical also. But he was writing right at the moment that that observational revolution was happening, and he was very skeptical about the epistemological status of those objects. He was like, well, the same way that scientists thought that spiral nebulae were observational support for those theories that at the 19th century, they could have they might be wrong. These objects could be different things and so on. So he came up with an interpretation that pointed to, first of all, there was no progress in the area. So he says something like, scientists are not able to answer the most basic question about the problem. Is the solar system formed by itself, or does it need an external entity to kickstart the formation of the planets and so on? And he also saw something that he calls it's a pendulum movement in the history, because he says, well, you had first, I didn't include here, but one of the first theories was nobody took it seriously, but Count Buffon came up with an idea in the 18th century that the planets were formed by a almost collision of a comet with the sun. So you can imagine the amount of I'm not going to say ignorance, but the lack of knowledge about these objects. Anyway, so Buffon thought that the planets were originated in an almost collision of a comet with the sun, and then you had a movement in which, so this is a dualistic theory, and then you go to a monistic theory, the nebular hypothesis, and then in the beginning of the 20th century you go to a dualistic theory, and then in the middle of the 20th century you go again to a monistic theory, and then in the 1960s you go to a supernova trigger theory, which is that stars and planets to form, they need the a closed supernova to kickstart the process. If there is a massive star that explodes near the nebula, then you have the conditions to form planets around star, because this would feed the original nebula with heavy materials. And then you go again to a monistic theory and so on. So he was very skeptical about all this stuff, and he says that, well, yeah, we don't know jack about these things, and we cannot explain how the solar system was formed. And so there is no progress. So this is an outstanding case of science making no progress at all, trying to understand the subjects. And he concedes that exoplanets could change the game, because in this history here, I didn't mention one of the things that was very important, was that in 1995 you had the first detection of an exoplanet around a sun-like star, and then this starts a whole trend of discoveries of exoplanets around other stars. We're now, I think, we have more than 5,000 exoplanets discovered, right? So yeah, so this was a revolution, and the discoverer also, Didier Queloz, just won a Nobel Prize because of this. So this was also part of this revolution, the fact that we are observing exoplanets around lots of different kinds of stars, and we are observing a lot of different exoplanets. And I was, at first, I was I was convinced by Brush that he was right, but then I had, like a hunch, and I started to not only have a lot of conversations with scientists from the field, but by reading a lot of the papers and the studies, I ended up feeling that, they had clear intuition that the area is making clear progress, right? And it was making clear progress in the 80s and the 90s. And I was thinking, well, this intuition, I'm also unable to avoid this intuition. I think the area is making progress, and it was making progress in the 80s and the 90s. And so I delved into it to analyze these things, and I came up with the conclusion that you have a lot of ways of explaining this progress, I think, but the main thing is that, first of all, the background knowledge changed profoundly in the last 100 years, and more in the last 30 years than the whole past. So we now know a lot more about molecular clouds, how they are distributed in the galaxy, the distribution of chemical composites in these molecular clouds, and so on. So the current frameworks are not in the same epistemological situation in which, the earlier versions were. And we now have observational evidence of formation of planets around stars. And I also make a criticism on Brush, because he adopts uncritically that classic categorization of monistic and dualistic, which is very anachronistic. Anachronistic is using a historical concept to, let's say, understand the past, but you're using it with, in a sense that does justice to what you're observing in its own time, right? So it is very anachronistic. Why is it anachronistic? Because this categorization was, created there at the beginning of the 20th century, and now what we know about astrophysics and astronomy point out to a situation in which there is no sense in separating theories between monistic and dualistic and so on. There is no meaningful way of categorizing these theories in that sense. There is no pendulum. There is no way of portraying this stuff in the way that brush does. But still, there is no general theory that can explain every step of the process in a way that doesn't conflict in some step with other concepts. Well, I already told you this, but I feel like the intuition of progress is not delusional, of course, and observation are guiding the general picture. The epistemological status of protoplanetary disks are not the same as that of the spiral nebula and so on. And now we have a specialized community that has, since a framework was established, a general framework was established, is very is astonishing the amount of detail that the community can examine the problem, and you have scientists that are specialized in a very narrow question. Let's say how planetesimals can grow from the size of meter to kilometer and so on. And this is leading to a lot of development that could only be interpreted as progress. But what kind of progress are we talking about? And this is more like to philosophy of science thing. So the thing is that when I was trying to justify my intuition of progress of the area, I couldn't in any way conceive this as progress towards some form of truth. It is very difficult to conceive any kind of scientific progress in this way. We have a hunch that science progresses towards truth, but it's very difficult to formulate explanations about this. And I came up with an adaptation of what this guy wrote. This guy is Thomas Kuhn, very famous philosopher of science. He wrote The Structure of Scientific Revolutions, one of the major classics of philosophy of science in the 20th century. And although his theory of science has a lot of problems, it is not sufficiently historical and so on, I think he has a very compelling view of how science progresses, which is drawn from a Darwinian concept, which is science moves away from unfit views, but not towards truth or definitive knowledge or cumulative knowledge or something like that, as it happens with Darwinian evolution. You don't have evolution towards something, you have evolution from simpler organisms, simpler structures in life. You cannot say that we are more evolved than a fly or a cat, especially. Right? I always have this in mind. So, to quickly wrap up, all I said, there are currently still major debates about how planets form. And there is still no self-consistent theory that that doesn't have any outstanding problems to explain all of the process of planet formation. But this do not tells us that the area didn't make any progress, right? This is not reason to believe that the area didn't make any progress. I know that talking about these things may be very strange for scientists and for people that are outside of philosophy of science, because philosophers usually worry about some things that are very, very, characteristic of philosophy. It doesn't have, that many repercussions to science itself, There is a Brazilian scientist that, usually said that philosophy of science is for science what erotic literature is for sex, which is a funny way of saying that, yeah, it can have an effect, but it's not mandatory to solve things in philosophy. But anyway, the thing is that what we have here is that, like sometimes philosophers, they go to an analysis which is kind of binary in terms of theory choice. They're always trying to examine the historical developments of science, separating, the stance of scientists towards a theory between, like acceptance and rejection, yes or no. So, and if you go to examine the history of science, you find a lot of instances in which scientists choose to develop a framework, to develop an hypothesis without being too much, believing that this is the true about what they're going after. The fact that they're developing a theory doesn't mean that they are just accepting it as the only way to do science and to investigate. And I feel like there is plenty. If you go to look at the history of these studies in the last 30 years, you have a lot of reasonable support for the choice of the community to develop a general framework. But this choice doesn't mean that, okay, so they solved the problem, they are in the right track, and we can be sure that this is the way to go to explain the origin of planetary systems and so on. We can never be sure of these things. That's what philosophy is all about. We almost never can be sure of anything. And I think this is a good way of wrapping up what I presented until now. Yeah.
You can keep it.
Oh yeah. Okay.
Just move to the middle.
Oh, move to the middle. Okay.
Okay, thank you so much. So, am I to understand that the whole, how many years was the PhD? 3-4 years?
6 years.
6 years. And then you are out, your understanding was it was useless, the philosophy?
No, yeah. So the thing is that I think, so to be completely honest with you here, in the middle of the process, I was always thinking, what does this mean? Why am I doing this?
But, okay, every PhD student
Think about, of course. The amount of suffering always gets you to ask these questions, right? But
basically everyone in science.
Okay, yeah. No, but in philosophy, I'm not a pure blood philosopher. I'm an historian, then I became a science journalist, and I like to write about science, and then I went to do a philosophy PhD. And I was always worrying about, not only why am I doing this, but is the end result going to be anything meaningful, for people to think about this stuff? And I don't feel like scientists from this area is going to check out the history, or is going to let me check if what I'm doing is rational or progressive. They don't usually go to philosophy to check if what we're doing is rational and progressive and so on. But I do feel like that in my analogy there about literature and so on. I do feel like these discussions help to enrich the culture itself. I think this is useful for... so this thesis got published as a book there in Brazil, and I wrote it in a way that I feel like, at least, most people would be able to read. I wrote it as a journalist. I didn't write it as a philosopher or something like that. I really wrote thinking about people that are not from academia to read and think about this stuff, right? And I think I was successful in that sense, you know, like, and it was published as a book. There are some friends already that read the stuff and they really like the result, you know, like in the way that it is good to not only read the book, but it's good to think about these things and and I feel like, you know, that they ended up understanding that science is very messy, but also very beautiful stuff, you know.
Yeah, definitely. And but also in a positive side, I think one of the things, there are a few scientists in the room, and we actually miss this thought process in current science.
Really, huh?
Yeah, I mean, we don't really think philosophically. We think, oh, how do we actually get money? That's what we are thinking all the time. How do we get a grant to do this very tiny portion of science that probably will publish one or two papers, maybe not actually a major paper, so it's not so much of a philosophical thing. But so thank you so much for taking us through both planet formation and also your philosophical thinking. Thanks. So now we'll take a couple of questions. Let's start from back there.
Do need a mic?
No, you keep the mic.
You were saying like a classification between monism and dualism is already out of date, but after the discovery of exoplanets, probably we can, as a historian, you can say now which state, monism or situation or dualism situation. If you stick to that, if you force yourself to stick to that concept.
Yeah, the thing is that I should have be clearer in my interpretation, because now I think it feels like I'm not positioning myself clearly, right, in this thing. I position myself in this thing. I feel like there are all the good reasons of the world to think that planets are byproducts of star formation, and scientists are warranted in developing these ideas. This does not mean that monism is right, because what I show in my work is that the concept of monism means that the process is just one isolated process from everything, right? But what we now have is a concept that points towards processes that the star formation process and planet formation, they don't happen completely isolated from the environment, let's say, the molecular nebula and so on. So the scenario now is like, it's both. The thing is that, in dualism, in the 60s, Brush uses the older version of the categories. There is in the 60s there was a review on the field that said that dualistic theories are open theories. So you're dealing with something that it's not like that it needs an external entity to interact with that nascent object to make the planets around the star, but it is open. It's an open system. It might interact with other nascent solar systems because these objects are very crowded. The stars are born in very crowded spaces of star formation, and they sometimes interact and they sometimes capture objects from one another. So this means that the old dichotomy doesn't make sense at all. And what I feel like is we need another category, other kinds of categorization, let's say, one thing. And the other thing is that if you happen to conceptualize things as monistic points towards the fact that the planets are byproducts of star formation, then monism is right. But monism is not right in the sense that we're dealing with open systems now. So the categorization doesn't make sense. Sorry.
Yeah. I think I get your point, but I get more and more confused. Yeah, thank you very much.
Okay, sorry.
We can discuss more once you get a beer.
Yeah.
More beer, yay!
More beer.
So, who wants to go next? Are there any other questions? Yeah, here from back.
Actually, you talk about the impact of observation and the wealth of data that we are getting now. But in the end, will the result, and I would say the theory, be driven by observation more than just the exercise of pure intuition like Laplace? Because in the end, right now we still don't have enough data to really know for the statistical repartition of stars with planets, no planets, what kind of planet, and for example, if our solar system is a freak or not. So, what is your opinion about the impact of observational science and how to reframe this theoretic construction?
Well, I feel like the exoplanet research and exoplanet observations, or at least getting data that points towards the existence of exoplanets, they're pointing to two directions. The one is that they're pointing to there are statistical analysis since the Kepler Space Telescope started to detect a lot of exoplanets that are giving scientists a high confidence that the overwhelming majority of stars have planets, statistically speaking. So this is one thing. So this gives a lot of confidence to a scenario in which planets are byproducts of star formation, right? But the other thing is that, okay, planetary systems are super common in the universe, but the thing is that the end result of a planetary system is completely, it's stochastic. It's not deterministic. So they do not have any kind of, do not have any kind of way of determining when a planetary system is going to have gas giants or, more like terrestrial planets and so on. And the observations until now is pointing towards the fact that the solar system is probably a freak, right? We are not getting any observation pointing to, we didn't find anything like the solar system until now. So, both ways, but I feel like, regarding planet formation, it is pointing towards, decisively towards the fact that planets are byproducts of star formation. But, if you ask, are planetary systems, what's the rate of formation of planetary systems that have habitable terrestrial worlds? We don't know.
Yes.
That is one of the things, right? We don't know.
And on top of it, the data are biased by our tools, because Kepler is very sensitive to hot Jupiter, close orbit, big things, and we could be missing a lot of interesting data.
Yeah, but Kepler discovered a lot of mini Neptunes and super Earths.
Yes.
And not a lot of hot Jupiters that are, like the gas giants that are, orbiting very close to stars. And that could mean that, hot super Earths and mini Neptunes are the most common planets. And an interesting repercussion for astrobiology is that there are some scientists that came up with an hypothetical kind of planet, an hypothetical kind of mini Neptune. They called it Haitian, because because they can conceive these kinds of planets as habitable, because they would have global oceans and an atmosphere and so on. So they could, examine the absorption spectra and try to distinguish if there are any biosignatures there. So yeah. So, but we don't know how common these things are.
Okay. Yeah. Basically, we may need more money for better equipment. Okay. Are there any other questions? Yes, Kelly.
So I have a question, and before I ask it, I want to make sure that I know what I'm asking. So at the start of your talk, I believe you said that you also did some kind of research or had interest in astronomy in media.
Yeah.
Is that correct? So I'm wondering, because last month there was a speaker here who talked about like bad science in media. Is there one TV show or movie that you think, oh, their astronomy was on point, and you would recommend it?
Ah, okay. Well, in this case,
Interstellar has much better science. Interstellar has better science.
I think Contact, the old Contact from Carl Sagan, you know, like it's very, very, you know, like precise. And I also like the Cosmos series, not only the original from Carl Sagan, but also the newer ones from Neil deGrasse Tyson. I usually listen to Star Talk from Neil also, you know, it's a very nice show. And I feel that Neil is the quintessential explainer. He can explain everything in a way that is very engaging and charming and so on. And what I'm currently doing is a research in how astrobiology is being portrayed in the media. So how the research that is linked to the search for life is being, you know, like represented in the news media.
Okay. Any other questions from here?
Okay, since you mentioned astrobiology, I'm quite interested in is there any connection between like astrobiology and your doctorate studies? Like what leads you to astrobiology?
In fact, I never mention astrobiology in my thesis, but it is everywhere. It is like the main concern of my thesis. Because when I started to think about these things, was that I was shocked to learn that there was a time when scientists really believed that the solar system had a catastrophic origin. When I met that book, The Mysterious Universe. It's a small book. It is a rare book, but you can find it, I think, here. And it's really very nice to to delve into this kind of popularization from a century ago. And when I read that, I was shocked by it, and I was thinking, well, okay, so if I go to see historically how this thing developed. What am I going to find? Am I going to find, like the possibility that science can again point towards a scenario in which we think that life is exceedingly rare in the universe? And then this was my main concern. Then I started to go, and this is why this thing like pluralistic views, anti-pluralistic views appear a lot here, because I'm worried about what picture of the universe we end up with, and if it is or not conducive to the existence of extraterrestrial life and so on. I am a huge fan of the idea of lots of inhabited planets around the universe. I think this, when I said that this stuff has major, deep philosophical consequences, is that it informs, it is in the basis of what we call astrobiology today. And of course, that if we find life or something like that elsewhere, it's going to be major philosophical repercussions. And the Copernican principle is that we are not special, right? And we don't know, still don't know if this is going how this is going to play out. We don't know if Earth is special, in which way Earth is special. Current scientific knowledge is pointing towards the fact that probably Earth is special, but we don't know in which way, And I'm a fan of the idea that we are wrong about this. I'm a fan of the idea that the universe is filled with Earth's inhabited worlds out there.
That reminds me of a quote saying it will be surprising if we're not alone, but it will be more surprising if we are alone. Yeah,
I think there's a saying from Arthur C. Clarke. He says something like,
yes.
It's frightening, the idea that that we are alone, but it is equally. I don't remember the order, but it is equally frightening if we are alone, and so it is both are equally frightening and astonishing.
Great. I mean, if you've been to Shibuya on Halloween, you would say we are not alone. It's the craziest thing you'll ever see. Great. I think we should wrap up here. But Danilo's gonna stay for another half.
Yeah, I'll be
hour
happy
or so.
to
Until we
chat
close
with you
down this
here.
place, we keep drinking. So feel free to talk to him. And thank you.